Good afternoon. During the last lecture, I introduced the definition of exponential map of a regular surface. So, if S is a regular surface and P is a point of S, and epsilon is the value provided by proposition 5.3, this is a proposition which ensures the existence and uniqueness of geodesics. Then the exponential map is the map defined on an open disk of radius epsilon in TPS with values in S, and this function is given by this formula where gamma v denotes geodesic in S with initial point P and initial velocity given by V. We also observed that the exponential map of a vector of length different from 1 can be written as a geodesic in terms of a geodesic having initial velocity a vector of length 1. Why? Because if a vector v in TPS has a length different from 1, then you can write it as r times u, where u is in TPS, u is a vector of length 1, and r is a number in the range 0 epsilon. Then using these properties of geodesics, you can prove that the exponential map at P of RU is equal to gamma UR. So instead of traveling for 1 unit of time along the geodesic having initial velocity equal to V, you travel R unit of time along the geodesic having initial velocity equal to U. I want also to recall the definition of normal neighborhood. This follows from proposition 5.14, which says that there exists epsilon positive, possibly smaller than the value from previous definition, such that the exponential map is a diffeomorphism from the open disk in TPS or radius epsilon onto O epsilon P, which is defined as the exponential map of B epsilon. This is what we call normal neighborhood, of P in S. The goal of the lecture today is to try to understand the relationship between geodesics and minimizing curves. Uh, in other terms, it is true that a geodesic is a minimizing curve, that is the shortest path between 2 points, and it is true that a minimizing curve is a geodesic. Okay, we need some other definitions and other tools. So the first thing I will do is to introduce a definition of normal coordinates and the normal polar coordinates. And I will use normal polar coordinates to prove a famous result known as Gauss' lemma. Okay, so suppose as usual that S is a regular surface, P is a point of S, then we can identify TPS with R2. How? Suppose that E1, E2 is an orthonormal basis of TPS. Then we can use the identification UE1 plus VE2 UV. This is a vector in TPS, and this is a point over 2. Now, suppose that epsilon positive is the radius of a normal neighborhood of P Then we can define the normal coordinates at P are the local coordinates UV corresponding the surface patch given by mu UV equal exponential map evaluated at U E1 plus V E2 with domain given by UV in R2 such that the U square plus V square is more than epsilon square. So in other terms, the surface patch mu is defined on an open disk of radius epsilon. The normal polar coordinates are defined using normal coordinates and making a change of variable. So we get the normal polar coordinates if we compose mu with the diffeomorphism F from R2 no, let's write it another way, defined by F of R theta equal R cosinus of theta, R sinus of theta. So in other terms, the normal polar coordinates are at P are the local coordinates R theta corresponding the surface patch sigma over theta equal exp of r cosinus of theta E1 plus r sinus of theta E2 with domain r theta in R2 such that r varies in the range 0 epsilon and theta varies in the range 0 to pi. I would like to observe that there is a problem while using this surface patch, and the reason is that r cannot be 0 because otherwise this is not a diffeomorphism, and when r is 0 you get sigma r theta equal, sigma 0 theta equal exponential map evaluated at 0, where 0 means 0 vector, and in this case you would get P. So this surface patch misses the point P. Now, as announced a few minutes ago, I want to prove the Gauss lemma. Which says that the vector sigma r sigma theta are orthogonal, but we can be a bit more precise than that. So let S be a regular surface and P be a point of S. Then the first fundamental form of the surface patch sigma, this one, has the form F1 equal dr squared plus g d theta squared. So in other terms, we have sigma r multiplied with itself is equal 1, then sigma r sigma theta equals 0. Okay, let's see how to prove this. So we have to prove that sigma r is equal to 1, that is E equal 1. And in order to do this, we consider the geodesic given by this map with theta fixed. I want to recall that sigma r theta is the exponential map at P of r cosinus of theta E1 plus r sinus of theta E2. So in other term, set u to be cosinus of theta E1 plus sinus of theta E2, and you get that this is exponential map at P of R U, that is gamma UR. So we are considering we need to compute sigma R, that is gamma prime UR. This is the velocity vector of this geodesic, gamma u. And this implies that sigma r is 1, because this is the velocity of a geodesic having initial velocity equal to u, which is a vector of length 1. Now we observe that sigma r is normal to S, because it is the acceleration of a geodesic and we use this fact to prove that f is 0 Okay, let's try to compute fr and prove it is 0. So fr is ddr of sigma r sigma theta, and this is sigma r sigma theta plus sigma r, sigma theta r. This is 0 because this vector is normal to S, and this vector here is in the tangent space to S. So this is 0. This term can be written as sigma r theta. I just reversed the order of differentiation, and this is equal to 1/2 d d theta sigma r that is 1/2 the derivative with respect to theta of e. But e, it is equal to 1, so this derivative is equal to 0. So this implies that the function r fr theta 0 is constant. We need to prove that this constant is 0. Show it is equal to 0. In order to do this, we write sigma as mu composite f, where mu is the first of the surface patches I introduced today. And I use the fact that the limit is r tend to 0 of the length of the vector f theta r theta 0. This is 0. This is a simple computation you can do. And use also the fact that the differential of the derivative of the exponential map at 0 is the identity. If you use these two facts, then you can prove that limit is r tend to 0 of the length of sigma theta r theta 0. This is 0. You can do this by chain rule. Derivative of this function can be written as the product of the derivative of the exponential map and this derivative here. So this implies that the limit is r tend to 0 over f r theta 0. This is the limit is r tend to 0 of sigma theta r theta 0 multiplied by itself. And this is 0 because of this result. So this implies that this is true. that is f is 0. Now I need to prove the following corollary. So let mu define on U with values in S, denote the surface patch for normal coordinates at P. Let 0 in U denote the origin. Then we have two statements. The first one says that the vectors mu u at 0, mu v at 0, and mu uv at 0 are orthogonal to TPS. Two, assume S is oriented and that the basis E1, E2 with respect to which mu is affine is positively oriented. If gamma hat with values in U is a regular curve with gamma at 0 equal the origin and gamma equal mu composite gamma hat has a unit speed, then the sign curvature of gamma hat Unfortunately, I have to erase this part. At t equals 0 equals the geodesic curvature of gamma at t equals 0. Okay, let's prove this result. One, we observe that mu VV zero V is the acceleration vector of the geodesic described by the following map. This implies that mu VV at 0, where 0 means the origin, is orthogonal to TPS. A similar idea can be used for proving that mu, so similarly, mu u at the origin is orthogonal to TPS. Now we have to prove that mu uv at the origin is orthogonal to TPS. Okay, the idea for proving this last statement is the following. We observe that mu uv multiplied by mu v this is equal to the derivative with respect to v of mu v minus mu u mu vv. Now let's observe that this is 0. This is consequence of Gauss lemma, so it follows from Gauss lemma that sorry, I have to be more precise. This is a 0 at the origin. I made a typo, excuse me. This is U. Precisely, Gauss lemma says that mu U mu V are orthogonal along the geodesic V is sent to mu 0 V. Some of you could complain in saying that the Gauss lemma has been stated using the surface patch sigma, but it's easy to understand why this is true. This follows from the fact that the map F we used for defining the surface patch sigma is a diffeomorphism. So if sigma r and sigma theta are orthogonal, also mu u and mu v are orthogonal. In the same and then, sorry, if this is, since this is 0, so let's, okay, sorry, I got confused. So one moment. So we proved that this is 0. This is 0 because the second term vanishes, because mu vv, which is this function here, at 0 is orthogonal to TPS. So this is a 0 at 0. Consequently, this is 0. So this implies mu u v comma mu v equals 0. Using the same idea, you can prove that also mu uv mu v where mu u is 0 at 0. What we proved? We proved that mu uv is orthogonal to, at 0, is orthogonal to mu u and mu v. Mu u and mu v generate span to tangent space, so this says that mu u v at 0 is orthogonal to TPS. Remember, all these statements about orthogonality are true only at origin. Now let's prove the statement number 2. Statement number 2 is the one about the equality between the sine curvature of gamma hat, sine curvature of gamma hat at 0. This is equal to geodesic curvature of gamma equal mu compose gamma hat at 0. In order to prove this statement, we write gamma hat as ut vt, and consequently gamma t, defined this way, is given by mu of ut vt. Now I need to compute gamma prime and gamma second. Prime means the derivative with respect to t. So gamma prime is u prime mu u plus v prime mu v. And gamma second has the following expression: u second mu u plus v second mu v plus u prime mu u plus v prime mu uv plus b prime multiplied by u prime mu vu plus v prime mu vv. Let me check if I copied correctly. Ah, yes. Okay, now we use the fact that mu u at 0, mu vv at 0, mu uv at 0 R orthogonal to PS. How? We consider the projection of gamma second at 0 onto TPS. Because of this statement, this is statement number 1, we get that this is equal to u second at 0 mu u at 0 plus b second at 0 mu v at 0. Please observe that there is a difference between the 0 which appear here and the 0 which appear here. This is t equals 0 and this is the origin. So this is a 0 vector. Now, why we need the projection of gamma second 0 onto TPS? The reason is simple. We know that if you have a unit speed curve like gamma equal mu composed gamma hat, this has unit speed by definition, by hypothesis, then the acceleration gamma second has a normal component plus a tangential component. If you want to compute the geodesic curvature of a curve on a surface, you look only at this component here. Why? Because this is kg times R90 gamma prime. So if you want to compute the geodesic curvature of this curve, gamma at 0, you evaluate gamma second at 0, and you try to compute kg by using this formula. So this is the formula for gamma second at 0, and this is R90 gamma prime at 0 that you can compute because I wrote it before. Gamma prime equal u prime mu u plus v prime mu v. So it remains to evaluate this formula at 0, and what we want to do is to compare kg with the sine curvature of the plane curve gamma hat equal ut vt at t equals 0. How to compute this sine curvature? Simple. You use the fact that in this case you have the formula gamma hat second equal to ks times r90 gamma at prime. So you evaluate it at 0 and you will see that Ks, which is given by this formula, coincide with Kg, which is given by this formula. Please pay attention to the fact that the R90, which is defined, which appears in this formula, is the map which sends the vector xy in minus yx. So it is the rotation of 90 degrees. Instead, in the counterclockwise direction, instead, this operator here is the counterclockwise rotation by 90 degrees with respect to the orientation you have chosen for S. I leave the detail of this computation for you. What is more important for us is a theorem 5.19. So let S be a regular surface P in S and O equal to normal neighborhood O epsilon P. Then every geodesic segment is uniquely minimizing. So this theorem here provides the first answer to the questions I mentioned before. It says that every geodesic segment, as long as it remains in O, is the unique shortest curve between the point P and any other point in O. Let's try to see the idea of the proof. I will not enter into the details. So suppose that sigma defined on U containing R2 with values in O containing S be the surface patch for normal polar coordinates so let Q0 in O different from P. Suppose that sigma is that Q0 is sigma of R0 theta 0, where R0 sigma R0 theta 0 is a point of view. Consider the curve gamma t given by P if t is 0 and sigma t theta 0 if t varies in the range 0 R0 closed on the right. Since sigma is the surface patch for normal polar coordinates, this curve here is a unit speed geodesic segment from P to Q0, and its length is of course given by this number. We want to prove that this is the shortest curve joining P to Q0. Show that gamma is the shortest curve joining P to Q0. In order to do this, we take another curve, so let beta be a curve in S such that the beta of A is P and beta of B is Q0. And there should be several cases to consider. In particular, we should study the case when beta is regular and the case when beta is a piecewise regular. But for simplicity, I consider only the case where beta is regular. because I want to explain only the idea of the proof. So beta in general can be covered with several surface patch, but here I will suppose that beta can be covered by only one surface patch, precisely the surface patch sigma. So I suppose that beta S has the following formula. I prefer to write this way. Okay, now I want to prove that the length of beta is greater or equal to the length of gamma, which is R0. So now let's compare the lengths of beta and gamma. So L is the integral from A to B of the square root of the first fundamental form evaluated at beta prime. So the formula is R prime T square plus G of R theta prime T square dt. The formula is this because if I use the surface patch sigma, then by Gauss lemma F1 is dr square plus G of R d theta square. So this is the point where we use Gauss lemma. Clearly this is larger or equal than the integral from A to B of R prime T dt. This is a positive term. So R prime square plus GR theta prime T square is larger or equal than square root of R prime T square, which is equal to the absolute value of R prime T. And clearly this is larger or equal to the integral from A to B of R prime T equal R B minus the limit as R tends to A of RT, that is RB. The reason why here I use this limit is that the function R of S is 0 when S is equal to A, because R of A is the distance, essentially is the distance the R of S is the distance of a point in U to the origin. Now we know that the distance function is not a regular function at the origin. So when we evaluate this integral, we have to pay attention. What is R of B? R of B is the distance between Q0 and the origin, which is R0. Why? Because beta B by definition is Q0. It's written here. Excuse me. I said something wrong. RB is the distance between Q0 and P, because yes, it's correct. So this is equal to R0. And then we can ask ourselves, when we have the equality between these two lengths, we have equality if this is 0, that is theta t equal a constant, it is clear that this constant must be equal to theta 0. What is theta 0? Theta 0 is the value of theta for which this was true. The function theta t, when actually it's a theta s. Okay, it's not a great problem. The function theta s takes the value theta 0 at b. So we know the value of this function at b. We are saying that theta t prime is 0, so this function will be always equal to theta 0. This is why this is true. And we have equality when this is positive. And if r prime t positive. These two conditions put together says that beta defined as sigma r of s theta 0 is a reparametrization of gamma, which has been defined this way. P if t is 0 and sigma of t theta 0 for t in A R0. This formula is similar to this one. The difference is that here you have R of S and here you have t. And we know that this is a function with the positive derivative, so this is a reparametrization of gamma. Please observe that there are other cases to be handled. Beta is a piecewise regular. 2. Beta is not covered entirely by sigma. So for this case, you use the same idea. You split the interval on which beta is defined on sub-intervals, on which beta is regular, and you use the same idea I used before on each of these sub-intervals. For example, you will write the length as the sum of integrals of this kind, and you will find that also in this case you have this inequality. For this case here, you have to use you have to pay more attention. Essentially, we have to split the interval on which sigma is defined on sub-intervals, and you can suppose that on each sub-interval beta restricted to the sub-interval is covered by sigma. And then you repeat the argument I used before. So this is true if beta leaves the image of sigma finitely many times. So beta leaves the image of sigma finitely many times. And then there is another case which is handled in another way. There is a case when beta leaves the image of sigma infinitely many times. In this case, it's possible to prove that if this is P and this is beta, sorry, if this is B, then beta nearby P is obliged to have this behavior. So beta is like spiral-like behavior, like spiral near P. And this is not possible because of the regularity of beta at t equal a. Remember that the beta at a is equal to p. And one more case which should be taken into account so case number 3, beta leaves Paul. Essentially you can use the idea I presented before to prove that if this is P, it is Q0, and beta behaves like this, this is all, then you can prove that this piece of beta, this is the part of the trace of beta, so length of the portion of the trace of beta inside O, precisely from P to the first intersection with the boundary of O is larger or equal than R0. And that's all for the proof of this theorem. So let's recall again what this theorem says. So theorem 5.19 says that every geodesic segment in O epsilon P beginning at P is uniquely minimizing. So I want to make a remark. Because of this statement here, it is now clear that O epsilon P coincide also with Q in S, such that the intrinsic distance between P and Q is more than epsilon. Why? Because this theorem says that if you want to measure the distances between 2 points, you can use geodesics. Because geodesics are the shortest curve joining P to any point in O epsilon. This result can be improved in fact. We have proposition 5.20 which says that a normal neighborhood O of P with sufficiently small radius has the additional property that it is contained in a normal neighborhood of each of these of each points in particular. Every geodesic segment in O, not necessarily beginning at P is uniquely minimizing this proposition says that if we take a normal neighborhood of sufficiently small radius, we have a stronger properties. We have that not only the geodesics beginning at P are uniquely minimizing, but also geodesics starting at any other point of O are geodesic minimizing. This is possible because this statement says that we can find the value of the radius such that the normal neighborhood of P is contained in a normal neighborhood of each of its points. So this means that you can apply previous theorem to any other point in this neighborhood. I will prove this result in the next lecture. That's all for today. Thank you for your attention.